Hello friends, today we will discuss argument principle. Argument principle. We know that what is meant by argument. Argument of z or f of z. What is meant by if z equal to x plus iy, then we know that mod z, that is modulus of z, is equal to square root of x square plus y square, and argument of z equal to what? Tan inverse of y by x. Tan inverse of y by x. So argument of z is the angle theta. Suppose this is your real axis and imaginary axis, and x plus iy is any complex number. If we join this with origin, then argument of this complex number z, x plus iy, is this tan inverse of this. Theta is tan inverse of y by x. Theta, if theta is the argument, then that is what? Theta is the angle made by this complex number or complex vector with positive x-axis. So there is a principal argument also. If minus pi less than or equal to theta less than plus pi, then this argument is called principal argument. That is lies between this to this. Okay, lies between this to this. Minus 182 plus 180. That 180. That is called principal argument. Okay. Now, so this is the argument of a complex number. We want to see the argument principle here. Before to see the argument principle, we need one concept in this argument principle, that is meromorphic function. What is meant by meromorphic function? That we will see firstly, and then we will move to argument function. Okay, argument principle. Now we will see the concept of meromorphic functions. A function analytic in a domain D, which is subset of complex plane, except possibly for poles, is called meromorphic in D. If your function is analytic except isolated singularities, that is except for poles, is called meromorphic in that set D. So meromorphic means what? It is not total analytic, but it should be analytic except some poles. Except some poles. That is, if we remove these singularities, then function should be analytic there. Function should be analytic. So that is called meromorphic function. So meromorphic function is a function which is analytic except possibility for some poles. Okay, that is the case. For example, suppose D is there and these are the A1 and A2. These are the two singularities, right, of the function f of z in this D. Then we say that this function f of z is meromorphic in D because it is analytic everywhere except at A1 and A2. In all other cases there, or in all other points, the function is analytic. That is the case. Suppose that f is meromorphic in D such that D contains set of all those points such that mod z greater than r. So D we are taking, suppose this is a circle having center something A1, radius r, and what we are taking, suppose that f is meromorphic in D such that D contains set of all those functions such that mod z, such that all those points mod z greater than r. Mod z is what? It is a circle having center at origin and radius r. So suppose D is your this one, and function is meromorphic in D. That means what? The function is analytic except possibly at poles. Except possibly at poles. Then the function f is said to be meromorphic at z equal to infinity. Then the function is said to be meromorphic at z equal to infinity. If gz equal to 1 by f of z is meromorphic in the neighborhood of z equal to 0. Again same thing is, if f of 1 by z is meromorphic in the neighborhood of z equal to 0, then f of z or g of z will be meromorphic in z equal to infinity. That is on delta 1 by r. Okay, that is the case. So meromorphic concept means what? It is analytic except at some point. Means at that point only it is not analytic, but all other points At all other points it is analytic. We will see some examples of meromorphic function. Then we will get the clear picture of or clear concept of what is meant by meromorphic function. For example, f of z equal to e to the power z upon z square. We know that. Now what about here? F of z has a singularity only at z equal to 0 of order 2, or pole at z equal to 0 of order 2. So z equal to 0 is the pole of this function. Except z equal to 0, now we know that the function is well defined. If z is not equal to 0, this function is well defined. It is also differentiable at z equal to 0. Z not equal to 0, it is also differentiable. That is, it is analytic. Means what? This function is analytic everywhere except at z equal to 0, which is the pole of this function of order 2. So f of z equal to e to the power z upon z square is meromorphic in C, whole complex plane, since f is analytic except at 0 all and in at all other points in C, and the singularity at 0 is the double pole. Singularity is double pole. So such a function are called meromorphic. So it is analytic everywhere except at z equal to 0, which is the double pole. Every analytic function in D, which is subset of C, is obviously meromorphic. Every analytic function is meromorphic, but every meromorphic function may not be analytic, isn't it? Every analytic function means a function is analytic at every point. That means it is meromorphic. Meromorphic means what? Function is analytic at every point except at poles. So analyticity implies meromorphic. But meromorphic may not implies analyticity. That is the case. Okay. So then sums and products of meromorphic functions are found. If we have two functions which are meromorphic, then their addition is meromorphic as well as their product is also meromorphic. F of z equal to 1 upon sin hz is meromorphic in again complex plane C, right? Since the singularities of f are poles at z equal to k pi I, k belongs to z. Now here, see this function f of z equal to 1 upon sin hz. This function is analytic everywhere except at those points where sin hz equal to 0. Where sin hz equal to 0. Where sin hz equal to 0? Z equal to k pi I. At z equal to k pi I. Therefore, what we are saying, f of z equal to 1 upon sin hz is meromorphic in C, except as only countable singularities are there, z equal to k pi I, like this. Further, similarly 1 upon sin z, this function is also analytic everywhere except at sin z equal to 0. Where sin z equal to 0? If z equal to k pi I, k pi. Where sin z equal to 0? If z equal to only k pi. Similarly cos z, where cos z is 0? 2k plus 1 pi by 2. At z equal to 2k plus 1 pi by 2. Similarly tan z is sin z upon cos z. Where cos z is 0? Again at this point. Cos z upon sin z. Where sin z is 0? At z equal to k pi. So all these functions are meromorphic since they are analytic in C except at poles. Okay. The function, this is also example of the meromorphic, e to the power 1 by z upon z square plus 4. Now this function is analytic everywhere except at z equal to 0, because at z equal to 0 e to the power 1 by 0 is infinity, that function is not defined, and z square equal to minus 4, that is z equal to plus or minus 2i. Okay, so what we are saying, but now see here, the function e to the power 1 by z upon z square plus 4 are meromorphic in C deleted from 0, not in C, because if we consider in C except at z square equal to plus or minus 4, it will not hold. So but except from 0, it is C, meromorphic in C except from 0, not in C. Okay, meromorphic in C because it is not analytic in at z equal to 0 also, and at z equal to plus or minus 2i also. since each of them has an essential singularity at origin. Because z equal to 0 is a essential. Because why it is essential? In the neighborhood of z equal to 0 also, there are so many points at which this function is not analytic. So as z equal to 0 is the essential singularity, it is not isolated singularity. Therefore, the function is meromorphic in C except 0, not in C. So, isn't it? So, a function is meromorphic if it has isolated singularities. If a function meromorphic in D, if that function has isolated singularities in D, not essential singularity. That is the condition. Okay. So a meromorphic function in C can have only finite number of poles in any bounded subset of C. So there should be only finite number of poles, not essential singularities. Okay, that is the concept of meromorphic. Now we will go for argument principle hour. Let F be a meromorphic in domain D. That means F has either F is analytic at every point in D, or it has isolated singularities in D, which is subset of C, and have only finitely many zeros and poles in D. Finitely many zeros also finitely many, and poles in D. If C is a simple closed contour in D such that no zeros or poles of F lies on C, then no zeros or poles of F lies on C, then 1 upon 2 pi I integral over C F dash Z upon F of Z with respect to Z, integral over C of F dash Z upon F Z with respect to Z is equal to number of zeros minus number of poles, where N and P denotes respectively the number of zeros and poles of F inside T, each counted according to their order. That means if Z equal to 1 is 1 0. Also, if Z equal to 1 is twice second order 0, means it is repeated 2 times, then we have to consider N as 2, not N as 1. So what this result says that is this is a relation between number of zeros and poles and integral. Zeros and poles and integrals. So if F is a meromorphic in a domain D, suppose this is something domain D, anything domain D, which is subset of complex plane, and has only finitely many zeros and poles in D. This has finitely many, I will call it as poles, and zeros are also there. Zeros, zero of a function, and we know that pole of a function means what? Z square plus 2z plus 1. This has a 0 means what? What is the 0 of this function? This has no pole, but this has a 0. This has a 0. What 0 is there? Z plus 1 equal to whole square equal to 0. That is Z equal to minus 1 and Z equal to minus 1. So Z equal to minus 1 is the pole of order 2. Is the 0 of order 2 of this function. So 2 zeros are there. Suppose F has finitely many zeros and also poles in D. Poles means what? There are some points at which the function is not analytic. There are some points at which the function is not analytic. Suppose Z square plus 2Z plus 1 upon Z. This function has 0 at Z equal to minus 1 and has a pole at Z equal to 0. So number of zeros are 2 and number of poles are 1. Number of poles are 1. If I consider it as Z square, the number of zeros are 2, number of poles are 2. Z equal to 0, Z equal to 0, and so on. So any function may have zeros and poles. Okay. Suppose a function has some zeros and poles in this region D, if C is a simple closed contour in C such that no zeros or poles F lie on C, they must lie inside C. Like this. Suppose C is this curve. This is the curve contour C. Then 1 upon 2 pi I integral over C of f dash z upon f of z with respect to z is equal to number of zeros minus number of poles. This is called argument principle. This is called argument principle. Okay, where n and p denote respectively the number of zeros and poles of f inside C, each counted according to their order. Okay, their order. That is, if it repeated 2 times, then we count it as 2. If it repeated 3 times, then we count as 3, and so on. Define capital Fz by small f dash z upon f of z. Then only possible singularities of this capital Fz inside C are the zeros of this f of z as well as poles of this f of z, and they are finite. So this capital F of z has singularities at f of z equal to 0 and at f of z has poles, because at the poles this function is not defined. If this function is not defined, f dash z upon f z is not defined, that is not analytic. So now capital F of z also has finite number of isolated singularities. Therefore capital F of z is meromorphic function. Okay, capital F of z is also meromorphic function. Therefore 1 upon 2 pi I integral over C of capital F of z is nothing but addition of all residues of capital F of z in C. Addition of all residues of capital F of z in C. This is because of residue theorem. This is by using the residue theorem. We know that if any function has singularities, finite number of singularities, then we have already proved it. Integral of that function over C is nothing but 2 pi I times addition of residues of that function at all those singularities, Now, if Aj is the 0 of order Nj of f, small f, and Pk, and what? Pk is the number of poles of order Pk of f, then what we are saying? Aj is the 0 of order Nj. Suppose A1 is 0 of order N1, A2 is 0 of order N2, up to so on. There are some zeros of f, because we have given that f has finitely number of zeros. Those number of zeros we are considering A1, A2 up to so on with respective order N1, N2 up to so on. Similarly, Pk, pole of order Bk, here is it is Bk. Bk is the pole of order Pk of f, that is B1 is a pole of order P1 of f. B2 is the pole of order P2 of f, and so on. Then f of z is given by z minus aj to the power nj into g1 of z, where g1 of z is analytic at z equal to aj and g1 at aj not equal to 0. We know that if any function f of z has a 0 at a, right, has a 0 at a of order 2, then how you can write capital F of z as z minus a square into some function g of z. We know that. So every function, if a function has 0 at z equal to a of order 2, then that can be written as f of z equal to z minus a to the power 2 g of z, where this g of z is analytic at a and it is not 0 at a also, that we have written. Since f of z has zeros at aj of order nj respectively, therefore f of z can be expressed as z minus aj to the power nj into g1z, where g1z is analytic at each z is equal to aj and g1 at aj is not equal to 0. Similarly, as f of z has a poles at bk of order pk, then that f of z can be written as z minus bk to the power minus pk. Now what we are writing there? Now this is for 0. And what about pole? If a function f has a pole at z equal to a of order 2, then that function can be written as 1 upon z minus a square into gz. Again, where gz is analytic at a and it is non-zero at a. It is non-zero at a. Okay, that is the case. So fz is nothing but z minus bk to the power minus pk g2z, where g2z is analytic at z equal to pk and g2 at pk not equal to 0. Therefore, now f dash z upon f of z can be written as, I will consider for this, f of z can be written in this way, also can be written in this way. In both ways, we will see that. What about f dash z upon f of z? Now, f dash z upon f of z. What is f of z? Z minus aj to the power nj into g1z, and in the numerator it's a derivative, d by dz of z minus aj to the power nj into g1z equal to, I will use u into v formula here, isn't it? U into v formula. First function as it is, derivative of g1z, that is g1 dash z, plus second function as it is, g1z as it is, derivative of this function with respect to z, that is nj into z minus aj to the power nj minus 1, nj into z minus aj to the power nj minus 1 g1z. Okay, that way. Take z minus aj to the power nj minus 1 common, you will get z minus aj to the power 1 into g1 dash z plus nj into g1z upon z minus aj to the power nj into g1z. You can take directly this, what we can say that, ratio also. First function divided by this term will be cancelled, g dash z upon g1 dash z upon g1z we will get. Then second, z minus aj to the power nj, so it will remains 1 z minus aj in the denominator, and g1z cancel, we get nj upon z minus aj, isn't it? nj upon z minus aj. Now as g1z is not equal to 0 and analytic at aj, similarly g1 dash z is also analytic at z equal to aj, right? And it is not equal to, you don't know that whether it is 0 or not. So this is analytic part now, and this is the coefficient of nj is the coefficient of 1 minus 1 upon z minus aj. We know that this is analytic part and this is principal part. Principal part contains only one term and its a power is 1. So can I say that therefore this function has a pole at z equal to aj of order 1. That is, order 1 means what? It has a removable singularity also. So as g1 dash z upon g1z is analytic at z equal to aj, therefore residue of now this f dash z upon f of z at z equal to aj equal to coefficient of 1 upon z minus aj, which is nj. That is the coefficient of 1 upon z minus aj. So residue of f dash z upon f of z at aj equal to nj, at aj equal to nj. Similarly, here residue of f dash z upon fz at aj equal to nj. Similarly, f dash z upon f of z by using the concept of pole, because fz we have taken z minus bk to the power minus pk g2z, and then numerator it's a derivative. It's a derivative is this one. So first function, derivative of first function minus pk z minus bk to the power minus pk minus 1 g2z plus z minus bk to the power minus pk into g2 dash z upon this term. If we take separate division there, we get minus pk upon z minus bk, because here in the numerator it is minus pk minus 1 upon minus pk. So you will get in the denominator, and this one is g2 dash z upon g2z. Okay, these two will be cancelled. As g2z is non-zero and analytic at z equal to bk, g2 dash z is also analytic at bk. Therefore, this is analytic part and this is principal part. We know that we can find residue of this f dash z upon f of z at z equal to bk. It is the coefficient of 1 upon z minus bk. Therefore, residue is minus b. So what we obtain? Residue of f dash z upon f of z at aj equal to nj. and residue of f dash z upon f of z at bk equal to minus bk, equal to minus bk, and therefore residue of f dash z upon fz at bk is minus bk, and therefore now this is capital Fz, and all these are poles singularities. Bk is also singularity, aj is also singularity. So 1 by 2 pi I times integral of f dash z upon f of z with respect to z is addition of all residues at aj as well as at bk. So summation over j of nj and summation over k of pk. That is number of zeros minus number of poles, capital N minus capital P. This is called argument principle. That means to find integral of f dash z upon f of z over a closed curve C with respect to z, then it is 2 pi I times number of zeros minus number of poles. What zeros and poles are there? They should lie inside the curve C, not on the curve. They should lie inside the curve C. Okay, that is the case. We'll see one remark. If in addition phi is analytic on D, then under the hypothesis of argument principle, we have 1 by 2 pi I integral over C phi z f dash z upon f z dz equal to, just you are multiplying by phi of z if it is analytic in D. As it is analytic in D, there will be no effect on this. So summation over j nj phi of aj minus summation over k pk phi of dk. You are multiplying only by phi z because phi z is analytic at every point. Okay, it is analytic since also it has no poles. Additional poles are there. It has no additional poles where aj and bk are the zeros. If it has zeros, then you will get that time it is zero. So that will not affect on this order. Under the hypothesis of argument principle, we have 1 by 2 pi delta C of argument fz equal to n minus p. That's why we are calling it as argument principle also, because there is argument. 1 by 2 pi delta C. Delta means change in argument of f of z over C is equal to n minus p. Now delta, we know that delta argument f of z. That means what? Argument of f of something z plus a minus argument of f of z. That is the quiz. That is, we have to take two arguments, z plus a and at f of z, or z plus 1 and f of z, or z at two different points in two different. Consider w is equal to log of f of z, as f is analytic on C and fz not equal to 0 on C, because under the hypothesis of argument principle you are saying. What means under the hypothesis of argument principle? Small f of z is a meromorphic in D if C is any curve, and then these are the only finite number of zeros and poles for that f of z, and if C is any curve, then all the poles must lie inside the curve. As f is analytic on C, because no pole is lies on curve, so it should be analytic on C, and fz not equal to 0 on C, so no pole or no 0 on C, therefore it is analytic on C and non-zero on C. F of z not equal to 0 in the neighborhood of C also. For any analytic branch of log z, log f of z, we have derivative of log of f of z is f dash z upon fz, 1 by fz into f dash z. Therefore 1 by 2 pi I integral over C f dash z upon fz dz equal to 1 by 2 pi I integral over C derivative of into dz cancels with dz, we get only derivative of log of f of z, 1 by 2 pi I. What is integral over C derivative of log of f of z? D of log of f of z means what? Log of f at upper limit minus log of f at lower limit. That is change in this log of fz at C. Change in log of fz at C. Here, change in log of fz at C denotes the increase in log fz when C is transferred once in the positive direction, and we say that logarithmic integral measures the change of log of fz along the contour C. Now we express log fz in this way. We know that your log fz can be written as log of mod fz plus I into argument of fz, because we know that log z is what? Log z is what? Log of mod z plus I into argument of z. In the same way, log fz is also there. Okay, where log of mod fz is a single valued, and hence changing log of mod fz as it is a single valued, So it remains as it is because it is a constant. Mod of fz is a constant. So it is equal to 0 as log fz returns to its original value when c is transferred. This observation implies that change in log of fz is change in this plus change in this, but change in this one is 0. So I times change in argument of fz over c. Thus, 1 implies that this is equation number 1. 1 by 2 pi I integral over c f dash z upon f of z equal to 1 by 2 pi I times change in log of fz. But change in log of fz is what? I times change in argument of fz. Therefore, 1 by 2 pi I into I, that we get 1 by 2 pi only, change in argument of fz over c. Change in argument of fz over c, where delta c of argument fz is the increase in the argument of fz along c. So if you have a curve, any curve c, then if we take one complete rotation, then we want to see what change in argument of f of z. Argument of f of z. Okay, that is the case. If f is analytic inside and on a simple closed contour c and fz not equal to 0 on c, that is there is no 0, then 1 by 2 pi change in the argument of f of z over c is equal to n, because p is 0 as f is analytic inside and on a simple closed contour. Therefore there is no pole. No pole means what? P is 0. If p is 0, then only we get n minus p. This term we get n, that is 1 by 2 pi delta c argument fz equal to n equivalent. Here there are some examples on this argument principle. Consider the integral I, which is equal to 1 by 2 pi I integral over c f dash z upon f of z dz, where c is the circle having center at 1 plus I and radius is 2. Center at 1 plus I, radius is 2. So what is C here? C is this circle having center 1 plus I and radius 2. Where is 1 plus I? 1 plus I means 1 comma 1. 1 plus I means which point? 1 comma 1. 1 plus I means point 1 comma 1. We know that. Suppose this is your coordinate system, real axis and imaginary axis, right? This is 1, 2, 3, 4. 1, 2, minus 1, minus 2, minus 1, minus 2. 1, 1 means here it is point. So center is this one and radius is 2 now. Center this one, radius should be what? 2. Radius 2 means this is 1 and this is 1. It should be the radius of that circle. Okay. So 2 radius means up to 3 here you will get. Such type of circle should be. It is such circle. Okay. So here it is 3 point. Okay, like that. Therefore, radius 3, center 1, 1 plus I. It is like that, right? It is such type of circle is there. So where C is this one. Now for this function f of z equal to z minus 2 upon z into z minus 1. Z minus 2 upon z into z minus 1. We know that this function had 0 at z equal to 2. 0 at z equal to 2, right? And this function has poles at z equal to 0 and z equal to 1. Z equal to 0 and z equal to 1. So for this function, number of zeros are 1 and number of poles are 2. So capital N is equal to 1, capital P is equal to 2. But we want to see how many of them are inside this curve C, right? So z equal to 2. Where is z equal to 2 point? 2 means 2 comma 0. So here it is z equal to 2. So this 0 lies inside this circle C. Similarly, where z equal to 0? Z equal to 0 is here. And where z equal to 1? Z equal to 1 is here. So zeros are also lies inside the circle and poles are lies also inside the circle. Right? Now, For this circle, 0 inside the circle, 1 is inside the circle, 2 is inside the circle. What about I? I is here, it is also inside the circle. Similarly, 3 is inside this, 3 is what? 3 is on the circle. Minus 3 here outside the circle. Minus I is here on the circle because it's negative y-axis. Are on the circle, that means not inside. That means not inside. Okay, this circle, not inside this circle. Radius 2. Now, for 1 now, I is equal to 1 by 2 pi I integral over c f dash z upon f of z with respect to a z n minus p. Number of zeros. Which are the zeros here? 1 is the zero, which is lies inside. And number of poles, 0 and 1. 0 and 1, they are also inside. 1 minus 2, it is equal to minus 1. So directly you can say that I is equal to 1 by 2 pi I integral over c f dash z upon f of z with respect to z is minus 1 there. Similarly, for second, this has 0 at 2 and poles at 0 and 1. Again they are inside, but zeros is 1 and poles is 2 because 1 is now here. Pole 1 is repeated 2 times. 1 minus 3 equal to minus 2. For third, 0 is z equal to plus or minus 3. Z square minus 9 equal to 0. And pole is z equal to plus or minus I. Plus or minus. How many number of zeros lies inside C? So no zero lies inside C. How many number of poles lies inside C? There is only one pole lies inside C. Therefore 0 minus 1 equal to minus 1. Equal to minus. In this way, you can obtain the integral there. Next example we will see. We know that cos z equal to 0 implies z equal to k plus 1 by 2 pi. That means what? Z equal to 2k plus 1 into pi by 2. We know that cos z is 0 at all odd multiples of pi by 2. At all multiples of pi by 2. That means at z equal to pi by 2 by putting k equal to 0. Z equal to by putting k equal to 1, 3 pi by 2, 5 pi by 2 and so on. That is all odd multiples of pi by 2. The only zeros of cos z inside the unit circle about pi by 2 is at z equal to pi by 2. If we take a circle having center at pi by 2 and radius how much unit? Only 1 unit. So the only zero of cos z inside the unit circle about pi by 2 is at pi by 2 and which is lies inside this, that is in center. Now what is the second zero of this function? 3 pi by 2. But 3 pi by 2 lies outside this circle because this circle has radius only 1 unit. Radius only 1 unit. It will go somewhere here. 3 pi by 2 somewhere here. Therefore there is only 1 zero. Isn't it? There is only 1 zero. Is there? Can we say that it has a pole of what? So cos z has no pole. Cos z has no pole. Only number of zeros are there because it is defined everywhere, analytic everywhere. So there is no pole. Therefore integral over such C whose center is at pi by 2 and radius 1 unit of tan z. How you can write? Again as it is, tan z can be written as sin z upon cos z equal to, what is the derivative of cos z? Minus sin z. So I will write this same function as minus integral over same circle d by dz of cos z. What is it? Minus sin z. Minus sin z into minus, we get plus sin z. So tan z, integral of this tan z over this circle is also written as integral of d by dz of cos z upon cos z with respect to z minus times. So minus as it is, but we know that if cos z, f of z has n number of zeros and p number of poles, if those zeros and poles lies inside this circle, then this integral is equal to 2 pi I times n minus p. So minus 2 pi I times n minus p. What is the number of zeros of this f of z inside the circle, unit circle? 1. And what about poles? 0. So minus 2 pi I times 1 minus 0, it is equal to minus 2 pi I. In this way, you can obtain the integral. In this way, we can obtain the integral. Some more examples are there. Tan hz is there. Over the curve z minus 1 equal to 2. This is a circle having center 1, radius 2. Tan hz can be written as sin hz upon cos hz. But we know that derivative of cos hz is sin hz. Therefore, it is d by dz of cos hz upon sin hz over same circle. Now we want to see what is the number of zeros of cos hz. But because for cos hz there is no pole because it is analytic everywhere. So cos hz has zeros only at z equal to something there. So we get number of zeros are 2 inside this circle and poles are 0. So we get 4 pi r. Similarly, derivative of this function is here. So f dash z upon f of z is here. How many zeros are? E to the power z minus 1 is also analytic everywhere. It has zeros at this point. When this will be 0, that is cos z e to the power z equal to 0, 1. When it is, if we z equal to 0. So z equal to 0, at z equal to 0. Whether this point z equal to 0, right? So here, this has 0 at z equal to 0. E to the power z equal to 1. So this function has 0 at which this is satisfied. At which this is satisfied. So z equal to 0 is a 0 of order 3. And therefore we get 2 pi I into 3, 6 pi. Because it is a 3 pi there. Because circle is a having center at z equal to 0 and radius 3 pi. Radius is what? 3 pi. So you take three terms there, then you will get this one. 3 minus 0 is equal to 6 pi. And similarly, all these are there. So you go through these examples and you will get such answer. Okay. This is also one more example. Consider f of z is z square minus 1. C is the circle having center at 1, radius is 1. If w is 1 by z, w is f of z, then for z equal to 2, w is 3. For z equal to 2, because it is w 4 minus 1 is 3. So w equal to f of z. For z equal to 1 plus I, if I take z equal to 1 plus I, w equal to minus 1 plus 2y. Why? If I put z equal to 1 plus I, z square minus 1, z square becomes 1 plus 2i minus I square. 2i plus I square. And this minus 1, right? So what you will get here? 1 plus 2i, I square is minus 1 minus 1. So 1 minus 1 and this one cancel. Minus 1 and this one cancel. We get 2i minus 1, that is minus 1 plus 2i. For z equal to 0, w equal to minus 1 by putting this. So this is your z plane now. In z plane, our C is the circle having center at 1, radius 1. C is the circle having center at 1, radius 1. Therefore 2 is point here, 1 plus I is point, 0 is there, 1 minus I is point. For z equal to 2, what is w equal to 3? So 3 is here. So this point 2 will goes at 3. For z equal to 1 plus I, 1 plus I goes to minus 1 plus 2i. This is minus 1 plus 2i, isn't it? Because this is 2i. What? Minus 1, 2. This point is minus 1. For z equal to 0, here is z equal to 0. W is equal to minus 1. So you will get minus 1. So the image of circle in z plane under this function goes to this type. Okay, goes to this type, this contour. Such type of contour is there. So it is not circle. It is somehow this contour. Since f of z bar equal to f of z its bar, we know this relation. And since the contour C in the z plane is symmetric about z axis, this circle is symmetric about z axis. The image curve gamma, this is image curve gamma, in the w plane must be symmetric about u axis. As this is symmetric about x axis, this should be symmetric about u axis. From figure, we deduce that the change in 1 by 2 pi times change in argument of f z equal to 1 by 2 pi times only 2 pi. But is initial argument 0, and if we take one round, then final argument is 2 pi. So 2 pi minus 0 is the change in the argument, that is 2 pi, and therefore 1 by 2 pi into 2 pi equal to 1. So 1 by 2 pi times change in argument of f of z is 1. as C is transferred only once in the positive direction, starting from a point and ending at the same point. Therefore, at initially, argument of f of z was 0, and by taking one complete rotation, the argument of f of z becomes 2 pi. Therefore, change in argument becomes 2 pi minus 0, that we get 2 pi. Also, f has two simple zeros as z equal to 1 and z equal to minus 1. This function has two zeros at z equal to 1 and z equal to minus 1. Why? Because z square minus 1 equal to 0 implies z square equal to 1, that is z equal to plus or minus 1. So two zeros are there. Okay. Only the zeros at z equal to 2 lie inside C. 0 at 2, z equal to 1 lies inside C. So it has minus 1. Minus 1 is a point here. So z equal to 1, which is a 0 of this f of z, that only lies inside. So capital N is 1 here. Capital N is 1. There is no pole for this function. There is no pole for this function. So what is the integral of f dash z upon f of z over this circle C? It is 2 pi I times n minus p. That is 2 pi I times 1 minus 0. So 1 by 2 pi, this argument is also equal to 1. So by argument principle, the value of 1 by 2 pi, change in argument of f of z is 1. And by this diagram also, by taking diagram, 1 by 2 pi times change in argument of f of z is also 1. So in both cases, you will get same result. You will get same result. Okay, that is the case there. So this is also one more example in which we have discussed something. That is, if your function is z raised to 4 plus z cube plus 1, right? This function we are taking. If z equal to x, with x greater than 0, f of z is x raised to 4 plus x cube plus 1. If z equal to minus x, then f of z has x raised to 4 minus x cube plus 1, because z equal to minus x is there. This can be written in this way, x cube into x minus 1 plus 1 for x greater than or equal to 1, because this will get same, x raised to 4 minus x cube plus 1, and that can be also written as x raised to 4 plus, this is minus times x cube minus 1, isn't it? Or 1 minus x cube is there. For 1 minus x cube, I will take 1 minus x into 1 plus x square, but when? If your x is less than or equal to 1 and greater than 0. If it is lies between 0 and 1, you will get, you can write this, and for x greater than or equal to 1, because we have take positive, it will be like this. Thus 1 and 2 implies that f z has no real roots. There is no real root. Further, there is no real root means what? If I take this is equal to 0. So when we say that this, if I take this is equal to 0, there is no real root, there is no real number for which it is 0. Similarly, this equal to 0, also there is no, if I take it is equal to 0, there is no real value of x. Imaginary, only imaginary values of x will be there. Further, if z equal to iy with y real, then f of z can be written as y raised to 4 minus iy square plus 1, and you will get simple calculations are there, y square, y raised to 4 plus 1 minus iy square, which shows that f has no purely imaginary roots. This also no purely imaginary roots also. On the other hand, if C is a part or a circle having center at radius r, center at origin, where theta is lies between 0 to pi by 2, we have taken arc of a circle, this arc of a circle, that is C taken round the part of the first quadrant bounded by mod z equal to r for sufficiently large r, then f of z can be written as z raised to 4 is this one, z raised to 3 is this one, and 1 is this one. Taking r raised to 4 e to the power 4 I theta common, you will get this as first 1 upon r e to the power I theta plus 1 upon r raised to 4 e to the power 4 theta I. This is a curve. If r is sufficiently large, then this will have approaches to 1, because if r increases, this will approaches to 0, this will approaches to 0, and so change in argument of f z is nothing but 4 times of pi by 2, 4 times of pi by 2, because you will get here r to the power 4 and e to the power I theta. So change in argument will be equal to 4 times of pi by 2, because this is argument is your pi by 2. Therefore, it is 2 pi as r tends to infinity. Similarly, on the y-axis, argument of f of iy is argument of means tan inverse of this function, f of iy. What is f of iy? F of iy is this one. This z for z equal to iy. F of iy is, this is the real part, this is the imaginary part. Tan inverse of minus of y square upon y raised to 4 plus 1 minus of y cube minus of, I think it should be y cube, not y. Y cube is minus. This is y cube and this is y cube. Okay. Yes. So minus of y cube upon 1 plus y raised to 4. Here y ranges from infinity to 0 along positive imaginary axis, infinity to 0. The initial and final values of argument of f set are 0. Thus the total change when r is sufficiently large is given by 2 pi minus 0, which means that there is a root lying in the first quadrant of this function. Lying in the first quadrant of this function. Okay. So by using this one, we can find the number of zeros, number of poles, and integral of given function. So this is the argument principle, which is very important in the complex analysis. So for at this stage, we will stop here, and next part we will take in next lecture.